Hello, everybody. Okay, go.
Cool, awesome. So how's everyone doing? Good. Okay, I see some familiar faces. We spent some time last week with them, so they may not, they may hear some things they've heard before. But this, the best way to end this seminar is looking at this a topic that I really care about and requires a lot of work to research, which is shortcuts for machine learning. How many people have pressed these keys in the last 24 hours? Only like half. I mean, we have some drinks there, so go get some. Yeah. So how many people have used this kid in the last 24 hours? Okay. How did you? Okay, maybe I should expand some because I see some people here haven't used the kids. How about in the last 1 week? No, never. Wow. Who's never used these keys? Okay. So how did you learn about these keys? And I'm here, very awesome. How did you learn about these kids?
High school.
High school. Wow. You love shortcuts. Okay, I love it. Even then the lecture is gone. Okay, high school. Like who taught really like for seriously? Like think who taught you how to use these kids? Your teacher? Yes. Why that some extra like break, huh?
It was friends.
Friends. Why did they teach you how to use those skills?
Well, because it was like, why would you be acting like somebody from the 80s when you could just be, more efficient?
Okay, more efficient, right? Okay. Another different reason. Yes.
It's on a personal level because I'm a keyboard user.
Oh,
So
that's a guy in maths too. Okay, why are you a keyboard user? What made you a keyboard user?
I am professionally bad. And I can use the mouse to make and copy and paste. So definitely this will be my go-to key.
That's amazing. That no one has ever given me that answer. I can't even ask you really other questions. So I'll tell you how I learned, and that's because I'm teaching the lecture, so I can pause, but it's really because my mouse died and I couldn't get a new mouse. And so you need to do some work and you force yourself to learn. So it's interesting that we use these keys very, very efficiently. And in my work, I currently use a Mac system, and I recently changed a little bit, and because I want to use those big monitors, right? And I started using this type of keyboard because it's nice. I can sit in the morning and close my laptop and I'm busy like this working, right? I kept making a mistake. The mistake was because of my Windows on my Mac was showing, this is an old like Windows keyboard, and I kept pressing like Control C, but it needed to be like Command C, and it was really frustrating me. And I started looking like, how can I change this? Then I don't want to mess up. And so this is a really good example of why shortcuts are life-saving, but they can really mess you up, right? We get very good at using them. In fact, most people don't even know Control Z, right? Which is the undoing of the errors that you make. And so they rely on these shortcuts. And it turns out that machine learning does the same. So I'm going to teach you about shortcuts today in learning. And I will give some examples. I'll try to explain them for you a little better, but I see you have an assistant. Yes.
The people online say it's better if you stand in front of them.
I don't need to be seen. The people who I want to see are in the room. So, okay. Okay, I respect that one. So describe some shortcuts and then sort of wrap around why we have a lot of different people here, why you should be interested in them. So this is a really good paper. It's done by Robert Gyros, and what he does is that he describes what shortcuts in deep learning are. This paper you can see was done in 2020. And don't worry about taking slides. This is being recorded, we'll send you, and I'm also happy to send you the slides themselves, okay? So, and that's the reason why I'm disclosing that is because I speak very fast. It just hasn't started, and then I don't wanna, like lose people. So Robert here described shortcuts in deep neural networks. This is important because it was 2020. It's a very good paper if you want to understand shortcuts. And what I'm showing on the screen are 4 different images. And the first one is caption the image. It's showing a green hillside. And when, the AI system is told to caption that image, it says that they're grazing sheep. On that image, they're not grazing sheep, but it relies on that all images I've seen with a green background tend to have grazing sheep. So I'm gonna guess that these are grazing sheep, okay? And so we tend to have these examples. The other examples are just showing any information, any image you give to an AI system. As we've all had, I think the people who've had any of my lectures, I've said AI does not say that it doesn't know, and so we find that AI is going to use the least painful way to learn something. AI also loves shortcuts, and then it's going to use those shortcuts to make its prediction. So the other examples here, I'll go through them a little bit, the radiology example, and also the text one. We kind of know it now because of GPT and the hallucinations that we're seeing with them. So this is a really good way to understand shortcuts. I'm showing 4 images. One has a camel against a green background. Do you think that those type of images are common? No, right? Camels tend to be behind the desert, right? Which is sort of like the 3rd image. Do you think we'd find a cow image in a desert? No, right? Because cows tend to be against, grass or something, right? And so shortcuts occur when you have another signal in your image that's consistent across all images, and those images, then that becomes a spurious strength. And so the deep learning model then learns about the background instead of the animal that you wanted to predict, because that's the easiest way to learn, okay? And so shortcuts are different from overfitting, right? Overfitting is when you don't have your machine learning model memorizes the data, right? So it learns everything and says, I have 100 patients. And then it's also different from the optimum, where we want it to learn the intended features. And it's in between. The shortcuts are not bad, actually. For example, we see age is a big factor for shortcuts, but age is an important factor, right? There's some diseases that are more common when you grow older. There's some that are common when you're younger. And then, for example, skin tone and melanoma, which is a cancer of the skin, that those diseases, you'd want the model to factor in the skin tone in its prediction, because the model will be more generalizable. So those are the things. So shortcuts are not bad. And we know this because we rely on them to make our lives more efficient and a little more, less painful and more productive. And so shortcuts are a factor of how we train machine learning models and dataset bias. So dataset bias is another example, showing a cow on an ocean, like on the beach. Also very rare examples, not impossible, but very rare. And then this other type of image, which hopefully most of you can agree that there's a picture of a cat somewhere there in that picture. But if I see someone frowning, but you could also say there's an elephant if you're in Africa, because of the texture of the skin. And this is because most of our deep learning models, although we're in the era of the transformer networks, just take features, as characteristics, but they don't have a relationship of where the object is. And this is a big difference for medical imaging, because in, cats and dogs, if you're training a breed model, you find that you can give your AI model may never have seen a specific breed. It may not guess the breed correctly, but it'll say this is a dog. But we don't see the same for medical images. And so this is a problem that exists across multiple data sets, text, gaming, and everything else. So this paper explains all those concepts. So I'm going to move now to examples in medical imaging. This is a picture I've used a lot during this visit, which is a pneumonia prediction. I'm showing some AUC curves and also some data sets. And the most important feature here is just the radiology x-rays, where you see that there are these hot areas that are synonymous with the radiographic marker. Now, this is not unusual. The technologist will put a radiographic marker on an image to tell you this is the left side, right? Because you can kind of see it's reversed, like how you'd think about it. And you see that this is a model that is being used to predict pneumonia. None of the saliency maps, which are these hot areas, are are overlying any of the lung areas, and pneumonia is a disease of the lung. So you should, when you see this, you start to get concerned because we don't want the model to be using something else that's not where it's supposed to be looking. And it turns out that in this example, the model learned which patients were coming from the ICU. And it's a good guess. If you're getting a chest X-ray in the ICU, you probably have pneumonia. And so you make a prediction and you're probably correct. And so this is what the model was doing. The lesson here is that we have to think about how we build our test data sets. For a long time, and this is going to be a problem, especially here in Africa, where we don't have enough data sets. They're very expensive to acquire. What we should focus on is to build these very good testing data sets. When we do that, what we do is that we can start to see where the model is looking at. And it gives an area for us to do research in the explainability area, which is helping us say, I see that this model doesn't work well for this specific subgroup of patients, more than trying to say, I'm going to collect data sets from all African countries. It's going to take years for us to do that, but we can have 10 chest X-rays from every country very easily and use those to make our own test data set. So factor in your development, your test data set, and spend more time there. And it turns out the test data set, you have to invest the time in labeling it well. We're doing some work which is validating AI that's deployed in the real world setting. And what we observe is that if you have errors, especially now as we use large language models to label data sets, then those errors perpetuate and even make your baseline model assessment different. What I'm saying is that for your training data set, you can tolerate noise. As long as you have a big data set, the model will still learn the right thing or whatever the signal is in the data. But for your test data set, you don't have to think about size. You can focus on small amounts of data but more depth in terms of diversity, and that's going to help you evaluate your models better. And that can be done by domain experts because you just tell them and then they're like, oh, here they had cases. They probably even already have a case log of them. So that was an example from radiology. Here's an example from dermatology. And on the top row, we have examples of melanoma, which is a cancer of the skin. And on the bottom row, we have benign lesions. And these two images here have some patch. Now, if you think this is just like a stick on the patient, okay? This is not unusual actually on medical images. And what this group does is to say, they observe that any image that the model learns the patch just the same way like the radiographic marker in its prediction. So when you remove the patch, the model starts to struggle because it's like, okay, is this benign or malignant? And so you have to be very careful about how you curate your data sets because most of the time you're going back to get an old data set. What's interesting is that further evaluation of this work, and I'll show you, is that the distance of the lesion matters. And if you think, like if I was to take a picture of everyone in the room, I'll try to center everyone, right? So that you're the focus of my image. It's not that, unless you're not very good at taking pictures, most people wouldn't be in the corner. So the model does not really learn how many patients, how many people are in the room. It just needs to learn, when I see a lot of things in the center, those are people, right? And so that's what it uses to predict. And so it introduces this concept that there are easy tasks for models to learn and there are difficult things for models to learn. And so a lot of people are starting to look at every layer of a machine learning model and say, wow, I wonder what the model is learning here. And then to also look at different loss functions to make sure that the hard to learn cases, the model doesn't stop training when the hard to learn cases are not mastered by the model. Now, I'll show you another example for radiology, which is pneumonia prediction for COVID-19. We know none of the COVID-19 AI models were helpful, despite a lot of optimism. And on the left here, it's a busy slide. There are two data sets, and one data set is made from chest X-ray 14. This is a very old NIH data set, and one person went to Git, COVID, all the publications, pulled the images and made a COVID-19 data set. So amalgamating, mixing and matching data sets, not unusual. For us, I could come to Vukosi and say, hey, do you have some chest X-ray? He'll say, I had a project 2 years ago, here are chest X-rays, right? So this mix and matching of data sets is very common. And unfortunately, these are actually called Frankenstein data sets. So they're very, very common. People will put them back on Kindle. People will put not Kindle, Kaggle, put them back for you to reuse. And because you just want a data set, you jump on it and you use it. But these data sets have such strong signals so that for this one, the prediction of COVID-19 was around the AUC of 0.99. But when you tested that data set on an external data set, it just dropped. But what was interesting is that data set 1 and data set 2 were both Frankenstein data set. So the authors do an interesting thing, which is use generative networks to say, convert this positive patient to a negative patient and vice versa. And then they look at the attention maps for where the model was looking at. And it turns out that the AI model was just following the radiographic marker. If L was the thing that made a patient positive versus negative, then that's what it followed. Now, it's interesting because there's quite a lot of work. People looked at shortcuts around COVID. And if you're very, very sick, you're going to be laying in bed, right? You may be intubated, and because you can't breathe, so people are not trying to transport you across the hospital, especially when there was no vaccine, no testing. They want you to stay in your room. So they bring a portable machine for you. So, people try to predict severity of COVID from chest x-rays. And it turns out the model just learned the positioning of the patient. It started to see patients who are laying flat, they tend to be more magnified on their picture. And that's enough to predict who has severe COVID or not, right? So it has nothing to do with COVID prediction at all. And so one other thing is that we always think, gee, I'm not giving this model the patient's sex or something else, but the models are able to pick up these signals in the data set. So one good strategy when you build your model is to change the last layer of your prediction if you're using convolution or neural networks, and predict something else. Of course, don't predict something silly like predict Judy versus Abby. Like it may be nonsensical, but predict something still related to what you think could be a factor. So the same group, what they did is looked at patient sex and projection, and you can see for patient sex, for the internal and external prediction, there's perfect prediction and generalizability, even if that variable was not provided. So this is another way of looking and investigating what other signals could your model be using in terms of its prediction. Now, I mentioned that you need very diverse data set, and this is an example of such a data set. It has patient factors, it has order factors, it has imaging characteristics. Those things are just like what scanner machine was used, what was the time of the day, who was the technologist, who was the person who was reading this, and looking at embeddings is very, very interesting. And we did a little bit of work, not too much during the event we had last week for the datathon, but looking at embeddings is important because you can see features. And this is a really, really, really useful skill. And it's an amazing way to use foundation models. We rely on it in my group quite a bit. And if I can convince most of you that there are big 3 clusters here, and you can see that in this place they've just overlaid imaging types, and then you go back and you overlay something else, for example fracture, and you'll see that most fractures tend to be in this green cluster. So it tells you that most fractures in this data set were acquired with one machine. So 2 things you can use this information is it helps you guide your your splitting test, right? So then you can say, okay, I'm seeing this cluster here, I'm going to test here, or I'm going to mix and match this type of variables for stratified sampling. And so what this group does now is pick all these factors and predict them. And the most important feature is pretty much this one on the left here, that you see the model has a perfect prediction for what scanner model is, and close to near perfect for the scanner manufacturer. Those, for radiologists, those are not important things for us because it's like saying, here's a Nokia phone, here's a Samsung, here's an iPhone. Now, some people in the room may prefer a specific phone, but if I took a picture, it's probably going to look the same across all these phones. And so when you're interpreting, you're not really factoring in the manufacturer, but these models are learning the subtle imaging characteristics that are acquired from every device. And so you find that things that are more important in the prediction, for example, the BMI or whether there's a fracture, they perform worse than these other random factors. And you know that most data sets will not have the same. So here's an example of histopathology. These are when you have a biopsy or someone has removed a part of your body, the pathologists look at it under a microscope. And one thing that shortcuts are called in other domains is batch effects. And these are differences in data caused by technical variations because the samples were processed at different times or places rather than true biological difference. This is actually very common in genomics data. And so you have to be very, very, like your batch, you have to just process them at the same time. So in this case, we have these 6 slides here, and A, B, C, D, E represent just different cameras. You can see some are brighter, some are darker. Those are very subtle differences, but they really are important for models. In fact, E and F are the same slide. One is just brighter and the other one is darker. And so what this team does, they try to predict the patient age, right? You shouldn't really tell the patient age from a histopathologic scanner. You know, there's not even anything here that would tell you unless you knew the you know, what body part, for example. You know, so patient age, the scanner type, the preparation date, and the site. And to read this, you know, sort of confusion matrix, you can see that, for example, the slide origin is near perfect prediction. It tells you exactly what clinical site this, you know, what was it, hospital A, B, C, D, E. And the place where it doesn't do very well is the scanner preparation date, where we find, you know, was it like they're looking at the year of preparation, was it 2015 or 2017? But it's much better than a human who would be able to guess these things. And so what you find is that these models are still able to predict, you know, things that are not really relevant for pathologic. Yes, maybe age would be relevant, but they're not really factored in by the pathologist when they do this. And, you know, and also if you look at this other group that also does like how you cut, if you are cutting a piece of meat or potatoes, the thickness of your slices, and the model is very sensitive to just you know, the slice thickness. And this is important because we are seeing a new revolution of these multimodal models. And what those mean is that they amalgamate multiple data sets. And what they do is that we know that for future tumor prediction, it's not just enough to say, here are the cells that I see in the patient that are high. It turns out your neighborhood or the cells that are around you matter more than even just the quantity of cells. And that's a computational problem. So in that case, you find that just based on the tissue thickness, the number of cells and the number of nuclei that could be counted varies based on the tissue thickness. That's not something that you, as the computational scientists, are really going in and working and trying to figure out, is this slice cut the same way as another? Although I know in some centers, they're starting to use robotics to try bringing precision in terms of cutting some of the tissues. But most of the data sets we'll be using are old, so that this is not something you can control. So most of the things, maybe I could point out what the shortcut was. And I like to use this to, you know, remind you that I've said, yeah, you know, the radiographic markers, the R, the L, those tell you where the images are. These are images of knees. To take them straight, you have to put a metal rod in between the knees. And these are from different hospitals. So this group, what they do is they go back and try to predict the hospital side. You can see their AUCs are 0.98, which is very, very good. And by the way, I haven't said my favorite thing. When you get your first model that says AUC is like 0.99 or 0.9 something, that's a suggestion of an error, and you should really investigate it. And, you know, you should not be walking around and saying, oh yeah, my model is doing good, something is wrong. And, you know, what this group, I think what was a big takeaway for me is when I started to look at the saliency maps, and by the way, these saliency maps are very unpredictable. But when I look at them, I look at this side B, and I'm seeing it focus the hottest areas in the knee, in the metal rod in between the knees, which reminds me that it's not one shortcut in your data set. It's more than one shortcut. And when you remove one, just like you're peeling an onion, there's another shortcut. And so trying to say you're going to remove all shortcuts in your data set is probably almost impossible. Now, the gold standard for us in medical imaging are segmentation. These are, you know, you draw the area where there's an abnormality. In this image, I show you pictures of a femur ultrasound. They're used to measure the estimate gestational age. And in this one, you can see that there's a yellow ruler. And when there's a yellow ruler, the model has a perfect prediction because the lesion is centered. Similar example that I gave with the taking a picture of everyone in the room with everyone centered. And when you remove the ruler, the model starts to struggle in its prediction because it's factoring in the centerness and where the image is concerned. And I mentioned that most imaging data sets, here are 4 public data sets: ISIC, lung cancer, BRATS, which is a brain tumor data set, and prostate. And the malignant lesion tends to be dead center in the field, or whether it's scanning or radiology. And so the models, it turns out that if you made the lesion behave like an eclipse that is just moving across the images, that the lesion that is farthest away from the center demonstrates the least performance. So the model, instead of learning the lesion, it starts to learn, you know what, those things that are farther from the center ones are the malignant ones, and the ones that are farthest are problematic. So actually, a colleague of mine from Mayo recently showed me deploying a model for melanoma using mobile phones. And when the picture, and you can imagine mobile phone taking pictures is not easy, right? If you have to take a picture of your leg or your toe, someone else either has to take it for you. But when you point there, you'll find that, when the lesion is centered in the field, 0.99 performance. When you just angle it a little bit, 0.1 performance. So this is what's going to affect models in the real world setting, and we need to be, but all these are open areas for research. These are open questions to be answered. Now, so far, I've been talking around deep neural networks, but we're moving to this era of foundation models. That's AKA ChatGPT, the parent of ChatGPT. And these models see a lot of data, so you would say that they are more robust to shortcuts. That's what my assumption would be. Or they also are trained, they have bigger parameters, and everyone around is trying to tell us they can reason and do all these things. So that's what we would think. But I want to show you that these models encode the same features. So here is using PCA maps or UMAP for sort of just visualizing features is very common. And I think people like it. I actually do think when I review papers, I find it more informative. So this is just a TechSpot deep learning. This is a DenseNet 121 model. We see that there are different peaks across diseases, but not much for sex and race. But when you look at the same data set, we still see the different peaks in diseases, the different hills are representing different diseases, but now we start to see different hills for sex and race. So they are encoding these features very strongly. Now, I met a colleague of our conference who said, you know what, let me show you this other example. And I think there are 2 papers about this. One ended up, the final peer reviewed, one ended up in Nature Communication. I think the reviewers did not do a good job of making the paper better. The message changed. I recommend to read the archive version. And the archive version is interesting because what they do is they pick up pathology, pathology slides, and they look at the markings on the slides. So for example, one says 3 centimeters. These are not unusual. In fact, they reckon that 30% of slides have some form of marking on the image. So then they start to say, what if we had 3 labels? One thing it's the same slide. One has a misleading label, one has no label, and one has a true label. And this is really, I think, an interesting area where we're starting to see vision, which is the images, come now together with language. And, they show that when you have a true label model, I mean, these are definitely before pathologic foundation models, the models, but we kind of also saw this behavior in our datathon last week, that the models have a perfect performance when they have the right label, the correct label. But when they have no label, they start to guess, right? 50%. And then when they have a misleading label, their performance is pretty bad. And so, this was interesting for me because everyone who's publishing about this, or the companies that are building this model, they're saying, no, these models can see, right? They can see what's in the slides. And so this to me is a really simple experiment showing that no, they're not seeing. And then they do something interesting, which is to say, because you can do the prompts, right? So you can tell the model, please do not look at any text in your image. Look at only the pictures, right? And it has no effect. So if the models were really understanding or seeing or being directed, then we don't see them behave the same way when it comes to these models. And so when, finally people, one of the reviewers of one of my grants said, shortcuts is a problem because you're not an engineer. True engineers, 10,000 ex-engineers don't get shortcuts. It turns out that that's false. They do get shortcuts. This is a model that is already approved, and it measures, osteoarthritis of the knee. Usually for most of us, because we are right knee dominant and right hand dominant, our right knee tends to wear out faster than our left knee. And so they just flip the image. And they only used 50 cases to show this example. And what I love about this work, it just shows you the power of the test data set. That if you don't have all the resources, all the GPUs in the world to do this, if you focus on figuring out the problem statement and the small test data set, you could do amazing science this way. And be careful of the Frankenstein data sets that I showed. And so this, when they flip the knee so that the right one becomes the left and the vice versa, they start to see that the right knee now is said, oh, no, it's better, and the left knee is more sicker. And so it tells us that even if we don't have the commercial model, that the model is relying on the knee, right or left knee. It learns that feature and realizes that that's associated with the severity of the osteoarthritis. So far, and I'm looking forward to the food, so I need to wrap up, so we can all go, right? And so far, I've been looking at things that you can see, right? One of our biggest papers, we published this in 2022, is that we showed that if I gave you a chest X-ray of a patient, and this is not, maybe in South Africa, yes, but like in Kenya, this is not a common concept, really. I could tell you with pretty much maybe 96% accuracy if it was from a Black patient, a white patient, or an Asian patient. And if this ability persisted when we started applying filters on the images. It wasn't because of a shortcut, and it wasn't because, that some groups of patients were sick or not. And what subsequently other people have done is do this thing called opportunistic screening from chest X-rays. So people can extract healthcare expenses, they can extract how fast you're aging, they can extract other diseases. And so I like to say that if you could get my chest X-ray, this one is not mine, but I have gotten chest X-rays, you could say I'm Black, or I use Black because this is a social and legal construct. It's not really that there's a biologic difference. I also put like Kenyan just to show how ridiculous this prediction is. You could say I'm female. You could say that I'm aging faster because my chest X-ray age is 78 years, while my real age is 60 years. And I live in a poor area, and I have COPD and congestive heart failure, and I'm going to be very expensive in the next years. Now, this type of shortcut is very, very difficult to detect and remove because they're not all disease characteristics. And we did this work that was published in Nature Medicine, where we looked at combination of sex, age, race, and sex and race. And we still looked at the in distribution, so that's your training data, and then out of distribution, which is your external validation data. And we started to look at fairness. And there's always a tension. If you have a fair model, you have to give up something. And that's usually either performance or calibration, and also the degree of encoding. And what we found is that many data sets in their prediction. So here are 4 predictions from chest X-rays. And we find if there's a null finding, which is just a normal X-ray, that the models really encode sex in that data set. For effusion, the same. That makes sense because the breast tissue is around where the pleural effusion would be. But we find that the models that encode demographic factors strongly tend to be the most unfair. And it doesn't matter. We applied 6 ways of removing this unfairness, including, removing the demographic information. That's called like adversarial debiasing. Sampling, maybe upsampling or changing or improving just general robustness. And we found that if you don't resolve the models that encode demographic characteristics the most, it doesn't matter what downstream you do, those still tend to be the most unfair. And then what was surprising to me was that just because a model at UP is fair, if you give it to me, Judy, in Kenya, it doesn't mean that it's going to be fair. And it's really because of a fault of the underlying shortcuts that are documented there. So, we find that, for example, if this is just a different paper that shows the same thing, that most of the features that are most important and are most unfair are either related to sex and age, but age to me seems to be the most troublesome for and sort of perpetuating biases, but this is really because of the strong shortcut that is present in there. So when I think so far, what I think so far from trying to say, well, I started from AI can predict the race of patients. I've done a little more work with even the new paradigms. What I think we know today is that AI is an excellent feature extractor, and you have to decide what those features are going to do. And here's an example that has nothing to do with AI. And I like this example because it shows you how you can apply this tool to answer an old problem. So here is these are survival curves, and this is a patient with a head and neck cancer. And what this group showed is that if you get radiation therapy in the morning hours, that's between 6 and noon, you tend to do better, you tend to survive better, right? And if you see this as a patient, then I would refuse an evening slot. You'd be wondering, are those people like bad who come in the evening, right? But if you start to think about it clinically, they don't describe it this way. It's because maybe in the morning you book children because they cannot be staying and waiting for radiation therapy all day and crying in the radiation era. But if you look at that, maybe the children tend to not have very bad disease or tend to have curable cancers in the cohort that you have, or maybe the patients who are in the night or in the evening will have day jobs. They cannot get time off, which also tells you that their living conditions is maybe they are also a little more poor, which we know that has an impact on cancer survival rates, or that the patients who are at night could be admitted. And if you're admitted, that means you're sick, right? You're not coming from home. So just the timing, something so simple like this, and you have to factor in how you anonymize your data set to make sure that these time components are preserved. It shows me the potential of using AI as a strong feature extractor to look at old problems that we still are puzzled by. Here is another example that my student came and said, you know what, I think that if you can predict who's going to get post-mastectomy reconstruction for breast cancer, this is someone when you remove the breast and you also reconstruct it, those patients do well. And I said, that's a shortcut because you have to figure out which surgeon can do the post-mastectomy reconstruction. So those surgeons may be in private hospitals, or the patients who are getting post-mastectomy reconstruction have early stage cancers. That's why they're surviving better. So if you don't really apply the same sort of feature extraction and figuring out why they matter, you're going to start publishing things that don't make sense, but people be like, oh yeah, this is good, but it really doesn't translate down to patient care. And so when, and we've applied this to a little bit of our work. I did show this where at Emory, we have a model that predicts intracranial hemorrhage, which just means bleeding in the brain. And we can see that this chart is very busy, but it's just showing all the possible dimensions that you can do. You can look at size, you can look at location, but the most important takeaway is that we'll notice that our model had the worst performance for Black patients and patients who are less than 40 years. So that was interesting to me. So I went back and told my postdoc, tell me who are these Black patients? It turns out that the Black patients tend to come through the outpatient and emergency room, but we knew the model was not working well for that subgroup of patients. And we know that the inpatients are patients who've had surgery. So if you've had surgery in your brain, you could probably have blood. And so we saw that patient group had a 10 performance drop. Then we looked at age clusters, and we noticed that in our data set, young patients tend to be Black and our old patients tend to be white, which again explains why our patients were having disparate outcomes. But this is because of the concept of intersectionality, that we don't have one identity, and we also have a changing identity across time. Sometimes you're poor, sometimes you're rich, sometimes you don't have insurance, sometimes you have insurance, and so that's why trying to figure out these parameters for medicine is very difficult. Then we know that our Black patients are afraid to come to the hospital. So they, and here's actually a new project that we're going to do, which is to say, did the patients come, but they're young? Like you just see a young patient and they're coming to the hospital. You're like, are they looking for drugs? Or like, go home, it's just a headache. Here's some migraine medication. We don't know, right? And it could be just a pattern of care. Or the patients go home, then they're like, it's nothing. It's just a headache, right? So they come late. So when they come, they have this type of hemorrhage called subacute, which is very difficult for the models to diagnose because they are used to bright, which is acute blood. And so we see that there could be a factor in delaying access. And finally, we noticed that because Black patients will tend to come with hypertension, and you tend to have this single compartment hemorrhage. Well, sort of older patients who had multi-compartment hemorrhage, we find that the mechanism, whether it's hypertension versus trauma, if you're in an accident, had a factor in the way the model works. It's impossible for anyone to regulate this. It just can only be figured out by this sort of iterative evaluation and thinking about the different subgroups. And the foundation models afford us an amazing way to think about this. Here's an example of our breast data set. And you can start to see that there's a cluster here. And if I show my radiologists, they'll be like, oh, those are breast implants. So you can easily start to figure out some small clusters in your data set where the model is not working well. So when I think about shortcut learning, I think we need a paradigm shift. And everything that you work on, whether you work on data sets, whether you think about labeling, whether you're merging multimodal data, where you're thinking about explainable AI, either using saliency maps or in this era of vision language models. I mentioned about task complexity and the challenge of thinking about intersectionality. All these papers that, every week now there's a paper that is trying to do biologic age or how you live forever, or the opportunistic screening of using imaging, looking at real world model performance and thinking about how models fail and how to incorporate domain expertise. Or if you're interested just about benchmarks and external validation, all these buckets demand for you to understand shortcuts. If you don't do that, you're not going to be, you will probably get a good paper, but that's going to be a useless application. And this is going to be super important, especially when we think about when I'm working in Tanzania or Kenya, most of the data sets are actually abnormal. That's the shortcut. Well, most of my data sets in the US are from normal patients. And so that's enough already for the model not to work well. And so here's a part of my team that I left this summer. I just want to say thank you. And so please feel free to contact me. This is a page, we post a lot of videos and content. So this year we'll have another datathon at Emory. If you're ever in the US or want to come, let me know. This year we'll be looking at just, embeddings, and we'll be doing like amazing work on this. But I hope you learned something new and see how AI models are able to use Control-C, Control-V.
I'll lead a bit of the Q&A maybe let's stop. Let's stop share so that we can look at the questions online as well. Thanks again, Judy. It's always very insightful. We'll open it up to questions in the room, and then we'll also go online. Okay, Lang.
So the datathon is going to be possible to participate online?
No, because I like to you kind of were there, but from last year we had a summer school, and if you're working on so let me one of the things, because we have quite a lot of students in the audience, one thing that I want to encourage you is to learn skills that can transfer, right? We're seeing I think even yesterday I saw a big concern that people are saying that there are no jobs for computer scientists as they're starting out, right? And because it's trying to train us more. And the challenge is that people think that you're not learning skills that are transferable. Everything that I've shown you could work on crops, right? Fertilizer, the image, you can just pretty much replace the medical imaging and crops and you'll find the same problem. And so try to learn skills that are reusable. And so from the same last year, I put all the videos from the datathon last year, which is just how to think about approaching medical AI. And some point this year, probably I'll release the ones from this year, but it won't be possible to be virtual.
Maybe yeah. Oh, maybe you can introduce yourself and then where you're from, and then ask them.
How is this applied in the context of synthetic data?
Maybe repeat the question.
Yeah, great question, and which also tells me that I need to update my slides because we've done a lot of work on synthetic data. 2 years ago, I would not have believed that there's a future for synthetic data. But we know that you can generate replica of data sets that match the underlying distribution of your data. And so especially when you don't have enough data. What I have, we've done two pieces of work. One was to look at the impact on the downstream task. So still, original data is king, but if you don't have it, synthetic data, if you understand the distribution of that data set, is pretty good. Secondly, with the diffusion, the DDPMs, those are very good for conditioning. So if you looked, and I think finally, I would say that I'm tying things about how to approach a project in medical imaging, even medical AI brief, like in this framework. If you could extract embeddings, it gives you a quick view of all the clusters in your data sets. And now you can figure out the label. So with a conditional data, like a synthetic data, what you can do is say, you know what, generate for me what you think is patient with a hip fracture on this machine, right? If your baseline model is done well, and then you can use those as testing framework. So I think today, I think synthetic data is a tool that allows you either to investigate more shortcuts quickly, if you already know what the shortcuts are, or makes your data set more robust for times of generalizability. But we know that if your synthetic data has a different distribution from mine, it still will not work. In terms of the model performance. Yeah.
Rather,
so the question is, would you rather choose real data set? I'm just repeating for the people online who will be missing lunch, but you know, for synthetic versus real. And my thing is that you should use both if you can. Yeah, because if you don't have, you know, if you're in resource limited setting, I think synthetic data presents this concept of model as a data set, because you can pretty much, like, if the original parent model is trained well, you can condition it on so many things that it becomes so robust for you to do the testing. And it can also guide a little bit of, okay, maybe I only had 5 examples, and if you figured out what those were, if your parent model is good, then you can start to say, okay, generate for me more examples, because it's very expensive to get good medical labels. So that's just the reality. So I think you'll use both. Oh, and by the way, there's a new guidance from the FDA. Right now, there's a paper that is talking about how to use synthetic data for regulatory purposes.
Yeah. Okay. Angela, you can unmute and ask your question. I think.
Hello, Dr. Judy. My question is what are the ethical concerns regarding the use of AI in medical imaging?
Wow. So the many, but the reality is that that ship has sailed. People are deploying AI, whether it works or it doesn't. So what I would say, there's the issue of bias and the issue of ethics, and actually the issue of fairness. And most people have gone back to describe bias as a statistical difference, that your outcome is different across groups, wherever those two groups are. And so you can have a biased model and deploy it. It doesn't mean that bias is bad, you know, and this is because if you link it with an ethical outcome, that's actually the best thing that could have happened. So one popular example that is given for this is to say, maybe I have a model that says, it says Judy is not going to come to the clinic. And the model it's not really, doesn't know Judy. It just assumes that Judy lives in a poor zip code or is Black, and that's the reason. So that's a biased model. But if you spend the time and call me and say, oh, Judy, hey, are you coming to the clinic? You know, and then you say, is there anything we can help you to come to the clinic? You could find out 2 things: that maybe Judy has a job that does not give me time off. Or the second thing is that Judy could also have a job, I don't have transport. So you could, instead of double booking, like how the aeroplanes like to do, so that you lose your slot, they could just keep your slot and send you an Uber for you to come to the healthcare system. So in this model, it's biased, but with an ethical lens of implementation. And that's sort of, if you were to think about that, the example that I showed you of a model that we've already deployed at Emory, that we are now seeing, it doesn't work well for Black patients and also young patients. And you know, this was never in the FDA, but you can't stop the model, but you can start to say what's unique about this population and use the same hypothesis to go back and extract to explain some of the differences. So that's how it's a hard question, and we cannot all agree on what a fair model is, or, and there are many, many frameworks, but that's how I would think about real world implication of bias and fairness.
Thank you.
Okay. From the room, introduce yourself and then, yeah.
I am Emory from the DSFSI. So in terms of removing screenshots from the data before even the model, I know, like, in terms of textual data, there are several frameworks that allow you to do data encryption, not necessarily exact text or similar text, which also has its own limitation in what source languages, because the embeddings, even determining what is similar or what is not that qualitative. So in terms of the medical field, are there similar frameworks existing that will allow you to ensure your data matches the balance between diversity and some form of similarity?
We're gonna summarize his question. It's very long. I'm making fun of Idris. We spend a lot of time together. So I think the short version of the question is, you see similar characteristics that could be in text, and you've seen several approaches that have worked in text. In medical imaging, do we have the same thing? And also you added another question about, do you have tools that can help you figure out your data set quality in terms of diversity, right? Idris, there's no diverse data set. That's just a fact. Just the same way that there'll never be a model that works 100%. You just have to really figure out when it fails, and then there has to be a human in the loop so far. And so what people have done is to look. The problem with shortcuts is that even if I collect them a lot, and my students know, when we discuss papers, I try to keep as many as I can, is that you never really know that it's a shortcut till you're in the testing phase. Unless you've read the space or are very intentional in how you're setting up your work, we never really think about that. But true to your question, we don't do enough research about data sets. And this is an amazing area for research, because there's so many data sets, they are messy, but you could just study them, right? You don't have to pay anyone to, like, you can just bring your expertise and time. You don't need a ton of GPUs, and you can study just data sets. And this is something that I started to do last year, because I was just like, there is such a big gap about what we know about medical imaging data sets. And then the second thing, there's, if you know the shortcut, you can use adversarial debiasing. And what you do is that you have two sort of pathways. One is learning the disease, let's say pneumonia, no-pneumonia. The second one is learning, is this black or white patient, right? And when it learns that this is a black patient, you penalize the model, right? So you're sort of like saying, don't learn this, don't learn this, don't learn this, just keep learning the disease, right? So that's been very popular. And then the second thing is there's also causal debiasing, and causal is just assumes that, so causality, which is very common in economics, is actually increasingly applied to machine learning, and that assumes that you don't know what the real impact, right, the causality of the relationship between variables. So if you could identify one, like age, and then you have something else, you could start to build your model to do the same. In medical fields, I think ultimately, to be honest, it's better to link an outcome that's clinical outcome. Because I'll give you an example. One of the metrics we use to test your heart function is called ejection fraction. It's a number. If it's above 55, it's good, right? It doesn't matter if you're 70 or 65, really. But if it's low, it's problematic. And it's the same, it can be done for renal function. The problem is, if you could link your label with your ejection fraction, then it doesn't matter the performance. We wouldn't be chasing the more state-of-the-art performance, because as long as you knew that the difference is like 62 versus 61, you'd leave the model as is, because it doesn't change the clinical management. So going the last step and saying, how do you use this information and how does it change management, can also remove the stress of trying to beat benchmarks and squeeze models, because then they are problematic when they come to real world deployment.
Okay, I think we'll go there.
Hi,
Yes.
For today's space, and we specialize in coordinating South Africa's capability in the satellite value chain.
Ooh.
So in particular, of interest is obviously on the image shortcomings to indicate that
Yeah.
we have something called that.
They're gonna be the same.
The observation.
Yeah.
So with the observation, as well as remote sensing, GNSS, we basically have to process this large volume of data, but you can never tell, as you say, what the shortcut is going to be. So, what recommendations do you have in an area where you're trying to analyze a national or a regional data set, and you're going to encounter such shortcomings? I think one of the key challenges, I suppose, with something like agri is that unlike humans that live for 50 to 100 to 120 years, with crops, you generally have seasonality. So you don't have that same track record of, say, like building a data set for an avatar or a meta-human, which can then tell you that there's something wrong with the course of data that you're taking on.
Yeah. Great question and great project. So the question here is, you know, how do you think about shortcuts in, for example, remote sensing that has unique features like short seasonality, and you wouldn't really have these types of data set. So first thing is to bring more eyes to it. And I don't know how as a company you do that, maybe it's through the, DSFSI, right? You bring more. There's no reason for our students to be working on imaginary projects when they could be studying real world data. Secondly, there's even a foundation more. I follow a lot of GIS people. This goes, like I told you,
before the new thing.
I think that one of the things that has been
I
interesting
remember
for me is
when
why
we
the
were
same
assignments,
topic is like
I
medicine and the
spoke
other
to
way around. So you can, to be honest, like today, what I would do is pull up some of the foundation models, extract features, and start to look at clusters. I think if you have the domain expertise, you're going to find a ton of like really good ideas from that model. That's like something you can do today. Now it's big, which most are suffering from, but what we've started to do is even just put like simple like k-means clustering and start to just very traditional, very classical machine learning approaches and starting to look at them. And I'll be honest, we're going to start to also look at graphs, right? Because graphs can start to say, here are some similar patterns. So it makes it easy if you have domain expertise to say, oh, I'm seeing something weird here, or I'm seeing something different here. Yeah.
Just going to go online before coming back in here. So the question is, can large language models exhibit shortcut learning?
Of course. Yeah, so they have the worst too, right? There's a ton of people who've looked at, first of all, the one example is like if you change the last, based on your token window, if you just change the last sentence, then it defaults on that prediction. We also know that large language models can infer, just based on their training data, they can say, oh, for example, I think the one paper that we published, actually very early evaluation of this use, and there's actually a paper by OpenAI released 2 days ago that is saying this is the future for at least Kenya, deploying OpenAI for medicine. I'm being dramatic, but I think it's an interesting paper. But what we see is that if you say, young patient with a cough and upper respiratory infection, and you add black, and then the model just decide this is HIV or not. So they rely on shortcuts, and there are quite a lot of examples of those. Yeah. Okay. Even gaming, by the way, like computer games, the AI model sometimes like does the reward hacking, and will even find a corner to hang out to hack the game and win. So yeah.
Okay. Yeah.
My name is Kwak, the team of Ghana. So I went on our prediction of concentration of alumina that cell because of dust and temperature. So we have to avoid it.
Yeah.
So I ended up with the generalization vector, which I published in a book. Now, put it into real production, as in real life production. And the model shifts so much that human intervention was always needed. If somebody hit my book in Saudi Arabia and pulled the generalization vector and used it, this person is going to have the same problem. Okay.
Yeah.
So I'm like, I gave up on real practical application.
Yeah.
Do you have that experience?
Yes, but yours is, I think you need to figure out what your human's performance is. What do you think what do you think the human did in the loop, right? You have a human in the loop.
Yeah, exactly.
Yeah. Yeah, but what skill, right? Like, because what the difference between me and you is that I know the skill that I need my humans to have, and I can tell them, be careful when you're doing this here, be careful when you're doing this here. Right? Then they're able to, so even if the model will not work well, but as long as I can provide education to the human, then it doesn't matter, because then it can generate. But what do you think the human?
Come to an online system,
Yeah.
you know, like 100 predictions per second.
Yeah.
Okay, so that becomes real practical
Yeah.
problems.
Yeah.
For such and what if you know if you've done such real practical applications?
Yeah.
What
Yeah. Yeah. Yes. So the first thing is that it's even not a model performance, it's the interface of how you bring the AI to the human. So if in our radiologists, like this week, I got so many messages from our bosses saying, we need these studies read, they're behind. If your doctor has to click something else, it doesn't matter, your AI system could be the best, they're never going to use it. So this human machine and the HCI component, for me, has been one of the most important factors to consider in terms of of performance integration. Secondly, has been that the AI solution has to tackle a specific value for the human. And those tend to be the gray areas. If the AI is just telling you the most obvious thing, or on both extreme, like this is a pretty bad disease or there is no disease, then the humans don't care. They don't find it valuable, so they will not use it. So we also know that when you have bad explanations, your humans get biased and their performance absolutely drops. And there's one last one.
Okay, there'll be a last question.
That's good here. So, social learning, it's quite scary. But I just thought, okay, look at how people use data segmentation to improve performance. So you take an image, apply transformation, rotate it, darken and whatever, and that leads to an increase in performance. That in any way related to shortcut learning?
Oh yeah. Yes. Yeah. When you do, the question is, when you do imaging manipulations and you and you improve robustness, most of the time it's related to shortcuts.
Okay.
Cool.
Right.
Thank you.
Okay.
But they're not always bad. I think we're ending on a sad note. Now, shortcuts, like you remember when we showed the keyboard and we were optimistic, what we don't know is how to harness their utility. And so that when they fail, how we mitigate that. That's what we don't know. And that's why I said, all those topics I discussed today, they're pretty much open research questions to do. These are pretty new area of research and requires a lot of thought to do it.
Okay. Thanks, Judy, for your time and your insights. Just to add a few things. Yes, we do have a program at the university for people who are interested in working with us in terms of data. We have the MIT 808 Big Data Science Capstone Project, and we typically get access to lots of different problems and data that comes from different spaces. I think there's been projects on identifying solar panels on roofs in the whole country, and pests in Mpumalanga using satellite imagery, identifying, I think, with Chijioke music copyright law on text. The whole point, again, is to give people that it's something to come up with a problem and just hypothesize it. It becomes very different when you meet reality. As Mike Tyson says, like everybody can have a plan until somebody punches you in the face. Right, it just becomes this part. So there's this part of something. I think there's this thing called like firefighting? Street fighting programming or computer science. Like you have to learn these things of understanding how you actually work practically, and you always have to be thrown into a deep end. Before that, everything is just it's completely theoretical. It's a very nice toy problem that you have or data set that you have, but as soon as you have to make it available either for other people to use, you start noticing all of these things. The other part with data science for social impact, what you'll find is that we release a lot of either our data and models publicly. And this is one of the biggest reasons why. We want people to throw rotten tomatoes at us, as many as they have. Why? Because that's when you start identifying things that you didn't see. Because as researchers, you tend to sit with the problem and the world kind of disappears, right? Because you're just going very deeply into this one problem for a lot of time. And then what happens is that when you now, again, make it public, somebody comes and says, but like, you know, there's these things. So on one part, yes, shortcuts are not nice to find, but then we should also be very happy if they get identified.
Yeah.
Right, as opposed to feeling that, no, why was that? Because we really want to have generalizability. We want to get to these things that people can use and can learn from in multiple ways. So yeah, I do suggest people look out for those. You can go to DSFSI.co.za, and then you can go to our Hugging Face. We have GitHubs and all those things to test some of these things, and it should be a thing that we try to go for on the part of having, yes, open science, but then in another way, it brings more eyes to our problems. To finish off, this, like, you know, Judy coming during the winter, starting our AI winter at the university, means that there will be a few more seminars before the end of the year. Some will be webinars covering, there'll be hopefully 2 more that are also going deeper into the conversation of AI plus health in different spaces with different kind of views of what you can do in these areas. And at the same time, you can also go to our YouTube and look at our back catalog for the last 4 or 5 years, because that's also the other thing that we do. We record a lot of these so that people can have access to them. And yes, there might be a talk that's given at Emory, and then there's people in the room who are from Emory who ask questions that are maybe contextual to Emory. The reason we also do those recordings here is that because there's questions that are coming from the room that are very different, right? Depending on where these things, they change. And that also becomes another piece that you can use. So you can find all of these. So thanks, and thanks everybody online. And then there is lunch. I was told, sorry.